Okay, ladies and gentlemen, so let's go ahead and take a look at our analytical methods for sketching the graph of a function. Again, strictly non-calculator, and then we'll check with the grapher at the end. So if I want to know about the increasing versus decreasing behavior and any local extreme or turning points of original function y prime is going to give me all that information. But because x appears in more than one spot, I have to use, it looks like, the product rule when I go to differentiate this. So we'll go ahead and differentiate term by term to generate my y prime. I'm going to get the derivative of the product of two functions is the derivative of the first function times the second function, and then plus the first function as is times the derivative of the second. So it looks to me like my y prime expression is going to be e to the x plus x e to the x. Raise your hand if you had that expression for y prime. Great. Are there any values of x for which y prime is undefined? I know that those will be critical values and possible turning points on my original function's graph. No, e to the x is defined for all reals, and x is defined for all reals, so it makes sense that their product then would be defined for all reals as well, even if I don't know what it looks like. Okay, so I'm pretty good with my domain. Next, are there any values of x for which y prime equals 0? I don't know. Let's set it equal to 0 and solve. It looks like factoring is our friend. We'll go ahead and factor out an e to the x. That'll leave me with quantity 1 plus x. By setting each individual factor equal to 0 and solving, using the zero product property, I'm able to determine my critical values. It looks to me like e to the x. Does that ever equal 0? That's always positive, so that never equals 0. That won't contribute any critical values. But 1 plus x would equal 0 if x were to equal -1. So it looks like I have a critical value at x equals -1. Let's go ahead and perform now a signs diagram chart, a sign analysis of my first derivative. Remember, on your Unit 8 test, you'll get points just for labeling your number lines each time you construct one during your analysis. You want to make sure you're labeling it. That'll remind you which function you're going to go back and perform your sign test on, and let me know what you're analyzing depending upon what the question is asking. So we'll go ahead and label this a y prime number line. On it, we'll put our critical point x values. It looks like -1 is the only one. And now we'll go ahead and perform a signs test. Go ahead and tell the class the convenient x value to the left of -1. What's the convenient x value to the left of -1? Savannah? -2, thanks. I can go into any expression for y prime. For me, it's oftentimes easiest to go into my fully factored form. So I know e to the x is always positive. Let's plug in -2. As Savannah suggested, 1 plus a -2 is negative. So our overall sign of y prime is negative to the left of x equals -1. Convenient x value to the right of x equals -1. Gabby? 0, sure. So we'll go into our y prime fully factored form. In for x, put 0, and I get 1 plus 0 is positive, so it looks to me like y prime does in fact change sign at this critical value, indicating y switches from decreasing to increasing and has a local min at x equals -1. So we've learned a lot by this first derivative test. All right, let's continue with our second derivative. And so I'm going to go ahead and import our y prime. We know that my y prime is given by e to the x plus x e to the x. Did I get that right? E to the x plus x e to the x. So y double prime, when I take the second derivative to analyze my concavity of my original function y, is going to be given by the derivative of e to the x is e to the x plus, and by golly, I get to use the product rule again. The derivative of the product of two functions is the derivative of the first term times the second plus the first term times the derivative of the second. So it looks to me like our y double prime expression is given by e to the x plus e to the x is 2 e to the x plus x e to the x. Are there any values of x for which y double prime is undefined? I know those will contribute possible point of inflection x coordinates. It looks to me like, no, again, e to the x is defined for all reals. The product of x e to the x will be defined for all reals. Are there any values of x for which y double prime equals 0? Let's see. We'll set it equal to 0 and solve. Looks to me like, again, stop, think, GCF, greatest common factor. I can pull an e to the x out, which will leave me with 2 plus x. I know that this first factor, e to the x, right, is always positive, so that'll never equal 0. That one will contribute any possible point of inflection x coordinates. The second binomial, however, 2 plus x, that could certainly equal 0. It looks like I've got potential point of inflection x coordinates at x equals what? Negative 2? At x equals negative 2? Awesome. Let's go ahead and make a y double prime. A y double prime sign chart this time. And on it, we'll put our potential x coordinate, or our potential point of inflection x coordinates. Looks like negative 2. All right, what's a convenient x coordinate to the left of negative 2? Peter?
Negative 3.
Negative 3. I'm down, so we'll go in for x, and we'll put in negative 3. That first factor of the x is always positive. 2 plus negative 3, however, is negative. So overall, it looks like we've got negative y double prime values to the left of x equals negative 2. Convenient x value to the right, Blake?
Negative 1.
Negative 1. Negative 1, and for x makes this factor 2 plus negative 1 is positive. So it looks like y double prime has positive value. What does this y double prime number line tell us? It tells us the shape of my original function y. Y must exhibit concave down, right, curvature on the interval negative infinity up until negative 2, and then switches to concave up curvature at x equals negative 2, and then for the duration of the function's domain, negative 2 to infinity. And so this tells us, second derivative tells us about concavity, the shape of y. All right, can we put it all together? You bet your boots. Let's be sure and put the x coordinates of any critical values on there, the x coordinates of any possible points of inflection, and maybe they'll leave a little space and grab an x coordinate on either side, right, so they can get an idea of what this graph looks like. So our last part, we'll go ahead and do a little xy chart to help us. And on that xy chart, we'll go ahead and plug in our x coordinate of the possible point of inflection was negative 2. Our critical point came from an x coordinate of negative 1, so we want to make sure we include those, and maybe one on either side, so I'll do negative 1, negative 2, maybe I'll put that negative 2 in numerical order. And 0 would probably be easy to evaluate, even though it wasn't a critical point, but it would be easy to evaluate my function, so I like to add that one. And then maybe 1, and we'll see where we are. Okay, so let's go ahead and evaluate with these and see if we need to get some more. At x equals negative 2, my original function y is equal to negative 2 times e to the negative 2. That is negative 2 over e squared. Recall that e is the number about 2.718. And so if I'm thinking about e squared, right, that's about 7.4. So negative 2 sevenths. Negative 2 sevenths would be about, right, about negative 0.28. Negative 0.3, I don't know. Again, we're just getting about here. Exactly, it's negative 2 over e squared. Negative 1, at x equals negative 1, my original function y equals negative e to the negative 1, that's negative 1 over e. Recall that, right, e is about 2.718, so negative 1 over 2.7 is going to be larger than 0.33 a third, so maybe 0.4, about, negative. And make that a little bit prettier. At 0, my original function y is 0 times e to the 0 is 1, 0 times 1 is 0. At x equals 1, my original function is 1 times e to the first is e. That is about 2.7. I know that one, boy. All right, we have round up. All right. So is this enough to make our picture? I don't know. Let's go ahead and see. Our scale looks like all the activity is happening in between possible point of inflection x coordinates, critical points, negative 2 to positive 1. So it looks like we don't have to go very large. I'm going to go negative 3 to 3. And we've got a point of inflection at x equals negative 2, y equals about negative 0.3. So at x equals negative 2, I better get a scale here. So my y coordinates are going from negative 0.4 as a local minimum up until 2.7 on this window. So maybe I could do negative 3 to 3 again. Here, 4 to 4. So So -2 comma negative about 0.3, so that's about here. -1 is a local minimum because y prime switched from negative to positive, and that's paired with the y coordinate of about -0.4. 0, comma 0. 1, comma e, that's about 2.7, so about here. All right. So I'm going to go ahead and put a little x there to show I mean to switch curvature at x equals -2, right? Comma -2 over e squared. I think I want one more point. I'm going to go ahead and put x equals -3 to see if I can get an idea of what's going on over there. So I'll pick -3 as an additional. That's not a critical point. It's not a point of inflection. I just want to get a little bit more information. So x equals -3. I would get -3 times e to the -3. That equals -3 over e cubed. Recall that e is about 2.7, so e cubed, right, is going to be less than 27, but -3/27 would be -1/9, and so that's around -0.1. It looks like we're shrinking and getting closer to that x-axis. And I could continue choosing values, getting -0.1, -0.05, -0.03, and so on and so forth. So it looks like we're going to level out there. All right, so here we go. Decreasing concave down switches to decreasing concave up, local minimum, intercept, and increasing concave up. So let's do it. Switch concavity. Oh gosh. So I'm trying to switch concavity at that little X mark, and I'm showing that like on a test or quiz just so you can do it. Again, that's not a College Board thing. That's just so I know that you know that I know that you know that's where I'm trying to switch concavity. Let's go ahead and go to the graphers and see how he did. So for my original y equals function, we'll go ahead and enter x, e to the x. Everybody, let's check. Gosh darn it, I'm excited. So we'll choose our x e to the x, and let's make our windows match so we can see how well we did. Looks like I did -3.5 to 3.5, and my y min looks like -4 to 4.5. And if I don't like the window, then I'll change it. So we're just going to get an idea and see how we did. And then the moment of truth, pinch of salt, decreasing local min, and then increasing afterwards. Hey, not too shabby. I think we did all right, given that we did all that non-calculator, strictly analytical methods, and then check with our grapher last. Raise your hand if you had the same qualitative behavior before we did it together. Did you get that on your own? So several sprinkling. It's an interesting function, right? We haven't seen ones like that, and it's pretty powerful that we can use calculus to get a graph that, well, is that accurate, right, without ever using a calculator. So that's pretty neat. Polynomials are one thing, but these transcendental functions are a different story. So that's the power of calculus here. The same power of identifying local extrema or global extrema using the first derivative test or the closed interval method is going to be our starting point for the optimization strategy today. When we find optimal solutions of problems in context, complete with units, we're going to use the same calculus techniques that we did abstractly with graphs on the xy coordinate plane, now applied to real-world functions, right? That model real-world phenomena. So that's super exciting to me, and I hope that you get a lot out of today's class group. All right. So in any case, make sure that you're considering your registration for the AP Calculus exam. The registration deadline is before spring break. That's next Thursday, March 17th. Some students have come and asked me kind of, you know, should I sign up? Should I not sign up? And again, that is an individual decision. I went ahead and compiled the data over the last several years, and if you're performing like an average of a B on assessments, then you should absolutely sign up for it. Students have performed very well on the AP exam if they're averaging a B or higher on assessments. B minus students have still done well. Once you get below that in terms of assessments, the performance doesn't correlate as strongly, and so I've had students that are below a B minus who have ended up doing well and not so well in the AP exam. So once again, if you're on the fence and not sure, please just swing by outside of regular class and be happy to talk to you about in private. Again, it's different for everybody, and there's no surefire way, but you'll have to make a decision about that by Thursday, March 17th. And it is a fair amount of money, but if you think about that you could earn 5 units of college credit, and most AP classes are just 3 units of college credit, but the AP Calculus AB exam is typically 5 units at colleges and universities across the nation. It's a good trade-off. So if you're on the fence, please come and see me outside of class. I'd be happy to talk with you about it. All right, I'm going to go ahead and pause the recording, and we're going to go ahead and take care of our homework check. Okay, ladies and gentlemen, so today we're going to investigate one of the main applications of differential calculus. What do I mean by differential calculus? Using derivatives, right? Using derivatives in terms of applications and how we can apply those calculus concepts to real-world phenomena. So here we go. We've got several tools that will aid in our optimization strategy. Optimization, like finding the optimal solution, whether that be a maximum in the case of if we're trying to maximize profit for a business, or a minimum if we're trying to minimize the amount of gas needed for a delivery route. So optimization is finding the optimal solution to a real world problem. So we've got the closed interval method. That was what we used last class for absolute extrema, right? Where we simply find the critical points and compare the y-coordinates at the critical points with the y-coordinates at the endpoints, and select the greatest function value attained or the least function value attained, depending upon what we're trying to do. So the closed interval method is just when we throw the critical points on an XY chart along with the endpoints, and then compare the y values and answer the question that was asked. The first derivative test, right, is when we make our y prime number line in our sines diagram. And so when we do a y prime sine chart analysis, that's the first derivative test. Okay, and the second derivative test we looked at last time, recall the second derivative test is if I know y prime equals 0, that would indicate a horizontal tangent, a leveling off on my graph, and y double prime was positive, indicating concave up behavior, we must have a local min on the y function. Okay, if however y prime equals 0 and y double prime was negative, that would be concave down curvature, then that means we would have a local maximum. So what's our closed interval method? It is compare critical point y values with endpoint y values to determine extremes. What's the first derivative test? It's make a y prime number line and perform a sine diagram analysis. What's the second derivative test? Second derivative test, 2 cases, y prime equals 0 and y double prime negative. That indicates the presence of a local maximum on y. And I better say y has local maximum. Alternatively, if y prime equals 0 but y double prime is positive, indicating concave up curvature, then we know that y must have a local minimum. I want you to know that these tools, right, are just different options that we have in our tool bag. Sometimes we'll use, they're not sequential or anything like that. Sometimes we'll use more than one. Sometimes we'll use elements of each, right, as we're trying to answer the question that was asked, depending upon what we're working with, what the function's like, what the domain is, if we can find the domain of that function, and so on and so forth. And so I want you to know that these work in collaboration, right, cooperation together. So we'll typically use more than one together just to verify our answer and make sure we know what's going on. All right, so let's go ahead and try some. Everybody find our Jethro example. Now, he comes from a long line of farmers, and they've got this heirloom fencing that they pass down from generation to generation. Let's suppose that it's Jethro's turn, and he has 1,200 feet of fencing. He wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? And so we've got a classic, right, optimization situation here, all bet idealized, right? But it's just for us to practice with our strategies as we get more complex. So let's go ahead and consider the shape of our rectangular field and our optimization strategy. If everybody find that one-page single-side handout, if you go ahead and read it, step one from our optimization strategy. I didn't get this from a book or whatever. I just kind of made it up as sort of a general approach that we could use. So what does step one from our optimization strategy sheet ask us to do loud and clear, please? Vivian?
Read the problem carefully and write down the quantity you are trying to optimize.
Thank you. And so in this first step, we're actually going to write down our goal. We're going to write down the quantity that we're trying to optimize. Kind of like back with our related rate strategy, we read the problem carefully and we wrote down our known rates and what we were trying to find. That provided our goal, right? We needed to write an equation that included that rate and quantity in the eventual function. Well, the same is true here. We need to write down our goal. We're going to write down the quantity to be optimized. At the end of the day, when the dust settles, right, what quantity will we have optimized? Well, in this case, what are the dimensions of the field that has the largest area? Well, we will have maximized area. Sometimes we'll be minimizing weight or minimizing cost or maximizing profit. In this case, we'll be maximizing area. So for step one, I want you to write down our goal, the quantity that we're trying to optimize. In this case, we're trying to maximize area. The reason I do that, or I ask you to do that, is that this is going to provide the focus for the rest of the problem. We're going to end up writing an area formula eventually. We're going to use relationships in the problem situation to rewrite that area formula as a area function of one variable, and so on and so forth. All right. What's our step two then ask us to do from our sheet? Loud and clear, please, Blake.
Draw a picture, label relevant quantities and variables.
Thank you. And so let's go ahead and see if we can't make our picture here. We know that Jethro has his 1,200 feet of fencing, and he's going to make a rectangular fence that borders a straight river. So I'll go ahead and draw my straight river in blue. There's a little bit of current. Not so slope field current, but some cute little duckies. And we've got our fence. We don't need any fence along the river. So we've got the green fencing. And then we can label with relevant quantities and with variables. And so let's see. I don't know the horizontal dimension of the fence, but I could label that unknown horizontal length X, and I could label that vertical unknown dimension Y, and then I'd have my fence labeled with relevant variables. Each of those quantities X and Y would change depending upon if he wants to make a tall, thin fence, or if he wants to make kind of a wider, going farther out from the river, but not very tall fence. Well, I shouldn't say tall, but not very large vertical dimension fence. All right, now let's go ahead and take a look at step three. What does step three ask us about, Jake?
Step three asks us to write a formula for the quantity you want to optimize.
Thank you. And so our step one, we wrote down our goal, we're going to maximize area. Step three then says, let's write an area formula. So based on my picture and the labeled variables, let's write a formula to represent that quantity to be optimized. In this case, area. So if we're trying to maximize area, step three, we're going to write an area formula. Area is given by, well, in this case, a rectangular pen has area of a rectangle is base times height. But in terms of my variables, what would that be? Right? What would that be? Gabby?
X times Y.
X times Y, I'm down, thank you. And so X times Y would be my area formula, right? My area formula. What's step four ask us to do? Peter?
We use relationships in the problem and are given information to write the quantities formula as a function of one variable and consider its summation.
Awesome, thank you. And so right now we have an area formula. Area is given by X times Y. That depends on two variables. What we're going to do is use relationships in the problem to rewrite this as a function of a single variable, a of x or a of y. My area formula is going to be rewritten so there's just x's in it or just y's in it. And typically it doesn't matter which you choose so long as we can chunk it down to a single independent variable and a single dependent variable, and we'll be able to answer the question that was asked using our tool bag. So what information haven't we used? What relationship in the problem is going to allow us to write that as a function of one variable? Right? What haven't we used? Allie with a Y?
We haven't used like, wait, what was the question?
What information can we use in the problem to chunk this down to a single variable equation? What haven't we used? Absolutely. So if we consider our picture in Jethro's fencing, we know Allie's told us we've got 1,200 feet of fencing. right? We got 1,200 feet of fencing. So as I look at that picture, it looks to me like that green length of fence, again, we don't need any along the river, has to total 1,200, right? 1,200 feet. And so what equation would relate x, y, and 1,200? Benton?
2x plus y equals 1200.
So 2x, because we've got bottom x length, top x length, and then the 1y on the vertical length equals 1,200 feet of fencing. Awesome. So let's use that now to rewrite this area formula as an area function. So here we go. So my constraint was the 2x plus y equals 1,200. If I want to make this a of x, I would go ahead and solve this for y, so I could substitute in with x's in my expression. If I want to make that a of y, I could solve this for x, and then plug in what x equals to have just y's. Which would you rather have in your formula? Or your function, rather. A of x or a of y? A of x, I'm down. So let's go ahead and solve this for y by subtracting over. It looks like y is given by 1,200 minus 2x. We'll go ahead and substitute this expression for y into my area formula, and now I'll finally have an area function of a single variable. So it looks like a of x would be given by x times, and it looks like y is 1,200 minus 2x. Great. Hooray! So I've got an area function of one variable, and we've completed Jake's step 4. A of x equals 1,200x. Well, almost completed it. We still need to consider this domain. Minus 2x squared. Is that right? Awesome. And now we'll consider its domain. So as I consider our function a of x, can we determine its practical domain? Well, x represents the horizontal length of the fencing here, right? The horizontal length of the fencing. And so the smallest possible length of fencing, right? If I use all of my fence up on that vertical dimension y, there'd be none left over for that horizontal dimension. And so I'm thinking 0 would kind of be the leftmost y value of my x domain. And then if I used all of my fencing up on the horizontal dimensions, top and bottom, and left nothing for the vertical dimension y, then when would x run out? Well, it would run out when I used 600 feet for the horizontal dimension, because then on top would be 600, on bottom of 600, that's used up my 1,200, and I'd be nothing left. And so it looks like practical domain for this situation would be 0 to 600 for x. We could get into a discussion about my endpoints. Do I want to use parentheses or do I want to use square brackets? Well, if I use square brackets, right, we could argue that when I use 0 feet of fencing for my horizontal dimension x, that's not going to enclose many animals, right? So we could make an argument for we should do parentheses here or square brackets, right? Because I could, you know, and we weren't very, very smart, and it didn't say that's with a slow farmer, but it may be, right? We could use that, and so we could do a square bracket, or we could do a parentheses here. We're going to have to do a y prime number line if we do a parentheses here for sure, versus I'm going to do it just to verify now if I do a square bracket. Again, if I used all my fencing up on the horizontal dimension, x, 600, right? There wouldn't be any left for the vertical dimension, so I couldn't fit any animals in there either, right? But we could make a case for whether to make that a parenthesis or a square bracket as well. In fact, I think we'll do both. We'll do a number line anyhow. All right, I'm going to go ahead and grab these and take them with me to the next page. So let's go ahead and pick up now where we left off, and we'll go ahead and use our tool bag methods. We've got closed interval method, we've got first derivative test, we've got second derivative test. We don't have to use all those methods, but I'm going to make sure I do a y prime number line to analyze increasing versus decreasing behavior. I'm going to do the closed interval method to throw my critical points on an XY chart along with my endpoint values and compare. And between those two strategies, I'll be confident in my final answer. So let's do it. Ready, go. We need first derivative to get our critical values. So go ahead and tell the class A prime when I call on you. What would A prime be given by? Paul?
Negative 4x plus 1,200.
So A prime is negative 4x plus 1,200. Are there any values of x for which A prime is undefined? No. Are there any values of x for which A prime equals 0? Well, let's solve. I get negative 4x equals negative 1,200. Dividing both sides by negative 4 produces a critical value. Uh-oh. I can get it. at x equals 300. You guys got that? 300? Awesome. Go ahead and construct the y prime number line. Bam! Label. Critical point x values. Looks like 300 is my only one. And the convenient x value to the left of 300, I'll go ahead and choose 100. When I put in 100 to a prime of x, any place, I'm going to get negative 400 plus 1200 is definitely positive. When I plug in x equals 400, into my a prime expression, I get negative 4 times 400 is negative 1600, plus 1200 is definitely negative. So it appears that a must be increasing up until x equals 300 feet, and then decreasing after x equals 300 feet, which would indicate the presence of what feature at x equals 300? Well, a must have a local maximum. Does everybody see that? A local maximum. Great. That's good news because my goal was to maximize area. To be sure, let's go ahead and throw those on our a of x t-chart and compare using the closed interval method. So if I decided to make that a square bracket, then I can include 0, right, on my number line, 300 on my number line, and 600. I'm sorry, not my number line, but my XY chart. Now I can determine the area, right, the area by evaluating my function a of x at the given x value. So when x equals 0, then my area enclosed would be 0 minus 0 is 0 square feet. When x equals 300, I can evaluate my area. It looks like 1200 times 300 is 36, 360,000 minus 309, 90,000 times 2 is 180,000. 360,000 minus 180,000 is 180,000. So 180,000 square feet. And 600, 1200 times 600, 672, 720,000. So I'm going to square 36,000 times 2 is 720,000 is times 2 is 0. So I'm getting 0. I'm getting 0 for that. If you want to do home screen evals, that's totally fine too. We'll use our home screen for our calculator to evaluate. It's just fine. Again, it's just that we're using the analytical techniques of calculus. We're not doing second calculate maximum or second calculate minimum, right? We can still use our home screen to eval if we need to. All right, so let's make sure then that we're back to our 5 was use our tools, right? Use our tools to answer the question that was asked. Number 6, make sure you answer the question that was asked complete with units, right? And so we have to go back to our original question. Was the question, what's the maximum area that we can enclose? No. The question was, what are the dimensions? And so depending upon what the question is, we want to make sure that's what we're answering, right? It looks like my area is maximized, right, when my horizontal dimension of the fence is 3. So it looks like 300 feet by, and now we have to go and figure out what the y value is. No problem. When x is 300 feet, then y is given by 1200 minus 600 is 600 feet. And so it looks like 300 feet by 600 feet are the dimensions of the field that maximize the area. And that's why we're going back to this, because the question was, what are the dimensions of the field? I hate to see students do the correct calculus work and then lose out on your answer points, or if it's multiple choice, because you select the wrong response, right? Because you're not answering the question that was asked. If they're asking what's the minimum value, don't put the x coordinate in the critical value. Put the y coordinate, right? The y coordinate associated with it, because we know a minimum value is a y value, and so on and so forth. And so you could be doing all the calculus right, and I want to make sure that you're getting your answer points. Great. What questions do you have about Jethro? Okay. Then let's take a look at another problem. Let's find the area of the largest rectangle that can be inscribed in the region bounded by the x-axis and the curve y equals 12 minus x squared. And so this was adapted from a multiple choice item. So it's not as long or involved, but it has some good elements here of our optimization strategy embedded within. So let's take a look. We're going to read the problem carefully and write down the quantity to be optimized. So find the area of the largest rectangle that can be inscribed in the region bounded by the x-axis and the curve y equals 12 minus x squared. In this case, go ahead and tell the class our goal. What are we trying to do in this case? What are we trying to do in this case? Michaela?
Maximize area.
Maximize area again. Good, thank you. So our goal is to maximize area, and thanks for writing that down. On your Unit 8 test, on the optimization questions, you can get points just for writing down your goal. What quantity are we trying to optimize? So we're maximizing area again. Next, we want to go ahead and draw a picture and label with relevant quantities. And so in this case, we're talking about inscribing the area in the region bounded by the x-axis and a parabola 12 minus x squared. Let's go ahead and get a little sketch of that. So I'll go ahead and there's my xy axes, and maybe a little bit bigger. And y equals 12 minus x squared. So parabola upside down, same steepness, but vertex shifted up 12 units, yes? And so we can go ahead and make a sketch of that. It looks like 0, 12 would be the vertex, and then upside down. And then within that region, we've got a rectangle. Wait, we're bounded by the x-axis and that parabola. I'll go ahead and do that then. And our rectangle is inscribed. So inscribed just means inside, right? Inscribed means inside. So we'll go ahead and draw a rectangle inside, inscribed. And we're trying to maximize the area of that inscribed rectangle. What are some things that can be used to help us? Well, we can say that the corner of that rectangle lies on my function. So this generalized point x comma y must adhere to the blue parabola's equation, y equals 12 minus x squared. Awesome. All right, so what's step 3 then ask us to do? Grace?
Write a formula for the quantity.
Awesome, let's do it. If I want to maximize area, I'm going to write an area A equals formula. As I look at this picture, however, right, while a rectangle's area is still given by base times height, it's not going to be the same as Jethro's fence. In other words, the base of that green rectangle isn't x, my x coordinate. Right? What's the base of this rectangle? 2x, right? 2x is the base of that rectangle, and then times that y coordinate would be the height of the rectangle. So this, in this case, the area formula would be 2xy. Awesome. What does step 3 ask us to do, Preston?
Write a formula for quantity you want to optimize.
And, oh yeah, step 4. Sorry, step 4.
Use relationships to problem and or give information for quantities, formulas, function, and variable.
Awesome. So right now we've got our area A depending upon multiple variables, x and y. We're going to rewrite it to be a formula, a function of one variable, just x or just y. And so what can we use to chunk this down to a single variable? Well, we know that that point in red, that arbitrary point x comma y, must adhere to the formula y equals 12 minus x squared. So what can I do? Well, we can replace our y with 12 minus x squared and generate an area function of the variable. So let's go ahead and do that. We get a of x equals 2x times y. Y was our blue parabola. 12 minus x squared. Yeah. So it looks like a of x is given by 24x minus 2x cubed. Did I do that right? 24x minus 2x cubed? Yes? Awesome. And we can consider its domain. If I take a look at this function and consider what x represents, x is the coordinate of this point. So my least most x value, right? My least most x value would be 0, right? And my greatest most x value, if I had a really skinny, tall rectangle, that would be x equals 0 by least most x value. If I let this point go along down to here and had a really short, right, a short squat rectangle that's wide, then its boundary would be this x-intercept. And so can we get that x-intercept value? Well, I think we can, right? We could find the zero of that function 12 minus x squared. So what's this point right here? Well, let's go ahead and set 12 minus x squared equal to 0 and solve. So x squared would equal 12. Oh boy. So x squared equal 12, which means that x to be plus and minus square root of 12. We'll just take the positive one in this case. Now, we could certainly reduce this. I know that 12 contains a perfect square factor, but I think leaving it as root 12 is going to be easier for subsequent evaluations. So I'll just go ahead and leave that as root 12. So my domain consideration is going to give us 0 up until root 12. All right, I'll take those with me. And now let's go ahead and perform our first derivative test. And so we're going to find our critical points. We'll make an A prime number line and examine increasing versus decreasing, right? Area values, and then select the maximum area that's attained. So let's go ahead and get A prime. So what's my A prime expression going to be, Nikki? Awesome. Are there any values of x for which A prime is undefined? No. Nice, well-behaved polynomial. Are there any values of x for which A prime equals 0? I don't know. Let's see. We'll go ahead and add over, subtract over. Negative 6x squared equals negative 24. Divide. X squared equals 4. Looks like x is given by positive and negative square root of 4. So it looks like x is positive and negative 2. Only one of these is in my interval that we specified, 0 to root 12. So I'm going to purposely just grab that positive one. And let's make our number line. So my A prime number line. On it, we'll put the x values of 2. Let's choose a convenient x value to the left of 2, like 1 into A prime. 1 squared is 1 times 6 is 6, and 24 minus 6 is positive. So it looks like we've got A prime positive to the left of x equals 2. Let's pick a convenient x value to the right of 2, like 3. If I plug in 3, is that before root 12? I think root 12 would be 2 root 3, and root 3 is about 1.73, so 2 times 1.7 is 3.4. So 3 is less than 3.4 something, and so it looks like we can choose 3. 3 in for x squared is 9. 9 times 6 is 54. 24 minus 54 is negative 30, so negative values of A prime. Great. This shows that A must be increasing before x equals 2 and decreasing after. Therefore, A must have a local maximum at x equals 2, right? Which is good news because we're looking for a maximum area value. Let's go ahead and throw that critical value along with the endpoints of my interval on an XY chart and compare. So here we go. The closed interval method, if we couldn't find the domain, right, we'd have to use that first derivative test exclusively, but we could find the domain, so we can go ahead and make an A of x chart and compare function values. And so it looks like we've got our endpoints, 0 and root 12. We've got our critical value of 2. And we'll get the corresponding y values here for my area. Here we go. 0 in for x, 24, 0, 0. So it looks like my rectangle has an area of 0 square units if my horizontal dimension of the rectangle, or that point rather, is 0. Well, that makes sense. 2 in for x. So 24 times 2 is 48. Minus 2 times 2 cubed is 2 times 8 is 16. 48 minus 16 is 32. So I'm getting 32 square units of area enclosed when x equals 2, the x coordinate of my point. Do you guys get that? For A of x? Yes? Let's do A of root 12. So A of root 12 would give me 24 root 12 minus 2 times root 12 cubed would be root 12 times root 12 times root 12. Root 12 times root 12 is 12, times one more root 12 left over. So I'm getting 24 root 12 minus 24 root 12 is giving me 0. Well, that makes sense too. If I had my x coordinate all the way on the x-axis, then I'd be enclosing 0 square units as well. So what have we learned? Well, we wanted to determine the area of the largest rectangle. So this time it's not dimensions, this time it's area. So will my answer be 2, right? Or 0, or 32? Well, it would be the area value of 32. So don't say, after all this calculus work that we've done correctly, don't go and say 2, right? Don't say 2 is the maximum area, or 2 maximizes the area. Say 32 square units is the maximum area possible in this situation. So 32, I'll just say square units since we're dealing with it in the XY plane. Awesome. That's pretty sweet. All right. What questions do you guys have on these first two? In this case, we went ahead and maximized area. Let's take a look at a different scenario. We'll hold off on this generalized semicircle with radius r. We've already done a couple of these inscribed deals. Let's go ahead and take a look at the open top box problem. So whenever everybody find your packet, we've got day 3 problems for optimization. Let's find the open top box problem. We'll take a look at this one together. So for our open top box problem, our task is to construct a box by taking a regular 8.5 by 11.5 sheet of paper, right? Or is it 8.5 by 11? 8.5 by 11, so a regular piece of typing paper, right? And we're going to cut out squares from each of the 4 corners, right? And then fold up the remaining flaps of paper in order to create a 3-dimensional box without a top. So we'll call it the open top box problem, right? Our job then is to use calculus now to determine the maximum volume that such a box could enclose, right, using this situation. So using a regular piece of typing paper, 8.5 by 11. All right, so let's go ahead and use this as a means for practicing our optimization strategy. So let's first start out with our quantity that we're trying to optimize. In this case, what are we trying to do? Are we trying to maximize area again? Gosh, I hope not. We just did that twice. What are we trying to do, Andrew? Maximize volume, comma, baby. So we'll write that down. Thank you. Let's maximize volume. And let's go ahead and do step 2, draw a picture and label with relevant quantities. So here we go. We'll make a box. Let's see if I can get our 8.5 by 11. So we'll do, if we had our 8.5 by 11, and then we went ahead and cut out squares from the corners of dimension x. So the red is going to be the disappearing map, right? So the red's going to be cut out, and then it's going to leave me with all of these flaps that we could fold up, right? And if we kind of took out those red squares and then folded up those flaps, can everybody kind of visualize in 3 dimensions what those look like? Yeah, old news? Okay, good. So there's our green box. Awesome. Okay, so what can we label here? Well, it looks like these red squares have dimension x, right? Awesome. And it looks like the width of my box came from a piece of paper that was how wide? Right? How wide was my piece of paper, Scott? Good, so we can label that hole was 8.5 inches. And the paper before the cutting was how tall, Blake?
11 inches.
11 inches, so we can label that. All right, all right. So we've got our paper, and then we're going to cut out side lengths, or squares of side length x, yes? And so our job is to now, in step 3, write a formula for the quantity to be optimized. We're trying to optimize, that is maximize in this case, volume. So we need a volume formula, V equals. In terms of my picture, I'm going to have a rectangular solid, a rectangular box. So it looks like my volume formula, in general, will be given by length times width times height. It's just that the length of my box is not 11, right? Once I cut out those squares of side length x, what's the length of my box? Right, what's the length of my box once I cut out those side length x? It's no longer 11, right? What would be remaining? Michaela?
11 minus 2x.
11 minus 2x, good, thanks for our length. So our volume will be given by 11 minus 2x. Our width then would not be 8.5, right? What would our width be now, Peter?
8.5 minus 2x.
Awesome. In blue, thank you. And then our height, it's going to be tricky to visualize. So our height is going to be what we fold up for our rectangular box. So what would our height be given by? Right? Danny!
S.
Thank you. Danny's all the way in the back. Thank you, Danny. So now we have a volume formula that right now is written with just x's. So we had our v equals length times width times height. So we can already rename this v of x, and it looks like our step 4 is taken care of. That's pretty bomb, y'all. So I get v of x equals 11 minus 2x times 8.5 minus 2x times x. Great. Okay, let's go ahead and consider the domain of my function, and I'll go ahead and rewrite this maybe as a polynomial. So can we make this look prettier? Yeah, let's go ahead and do some multiplying here. So I get v of x equals 11 times 8.5, right? It'll be 88 plus another 4 point, oh, plus another 8, so 90. Six and a half? What are you guys getting? No. 93.5. Yay. Thanks. Minus 22x minus 16x is minus, nope, 17x. 17 and 22, 39x. Is that right? Is making this prettier? Plus 4x squared. And then times my x on the back side. So finally, looks like v of x equals 4x cubed minus 39x squared plus 93.5x plus u. Did I do that right with the FOIL? Are you guys getting that? Yes! All right, let's go ahead and grab this bad boy and consider our domain. In the context of this problem, right, in the context of this problem, what domain makes sense? Well, as I consider what x represents in my v of x formula, that's the side length of each square that will be cut out. So as I start cutting, right, the x side length could run from 0 if I did, right, the smallest square up until, what's the largest square I can make before I run out of paper? Cutting, right? What's the largest square? Is the largest square 8.5? No, I'd run out where, Jake? 4.25, I'm down. So let's go ahead and get our practical domain here. This would be 0 up until 4.25. Awesome. All right, guys, let's do a first derivative test and see how it goes. And we can use a home screen or a graph or two in case this polynomial gets ugly. So v prime, go ahead and share with the class what I call it new. So what's our v prime going to be given by? Page?
12x squared minus 78x plus 945.
Awesome, thank you. Are there any values of x for which v prime is undefined? No. Polynomial, smoothly well behaved. Are there any values of x for which v prime equals 0? Let's see. I've got a 93.5 here, so I'm not even going to try to factor. Instead, what I'm going to try to do is how do I solve a quadratic equation in standard form that equals 0? Quit? No, quit. Quit's not an option. Yes, quadratic formula. Let's do it. So I know my solution is x will be given by the opposite of b over twice the value of a. So opposite of b over twice the value of a plus or minus the square root of b squared minus 4 times a times c, close radical all over twice the value of a. And right about now is when I'm ready to go to the calculator. And so again, I'm trying to do this on home screen though. I'm not doing second calculate maximum or second calculate minimum on my home screen. I'll just evaluate that, and I'll probably raise a single fraction. I'm used to advanced algebra as having it split as the two, but if I'm going to eval on my calculator, opposite of b might be the easiest if I do one whole numerator and then divide it by 24. So here I go. Opposite of b, square root of and I just did 78 squared because I know negative 78 quantity squared will be the same as 78 squared, and then I don't have to mess with parentheses again. And when I do this, I'm getting 4.915, right? So is that good or bad news? That's bad news, right? This x value, right, doesn't help me out at all. How come? Michaela?
It's above the domain that we created.
Absolutely. It would be, I've used up all my paper at 4.25. 4.9 inches would be past my allowable square size. So I can't, right? I can't use this x value as a critical value. It doesn't help me at all. So I quit. No, I've only done the plus. I haven't done the minus in my quadratic formula. So if I go ahead and pull up the previous, and then put minus here, stop. Ah! 1.58. 5, that looks good news. And so it looks like we've got a critical value here. Now what am I going to do? I'm going to store this. Right? I'm going to store this in my graphing calculator so that I have those decimals and I don't have to, right, type it in at each time. That would be a real pain. So I'm going to store this now, and I'll store it in, what do I want to store it in? Alpha x? No, because then x will be like x. I'm going to store it in alpha a. So I'm going to store this in alpha a. That way I can just pull up a anytime I want to evaluate something with using this critical value, about 1.585 inches. You guys good? All right, so here we go. STO, isn't that sweet? STO, store. All right, you guys, let's go ahead and consider a v prime number line. On my v prime number line, I'm going to go ahead and put my alpha A. And I'm going to go ahead and perform a sign chart analysis. So let's choose an x value to the left of 1.585. I'm going to pick it 1. So if I do 1, I get 12 minus 78, right, would be negative 66 plus 93 is going to be positive. So I'm getting positive v prime values to the left of 1.585. I'm going to choose a convenient x value to the right of that. So I'll go ahead and do 2. 2 squared is 4 times 12 is 48 minus 156. 48 minus 156 is, any close? Negative positive. Want me to do it? I'm going to get it. Verify negative? No? Alright. Let's find Friday Blues. So I just went ahead and plugged in 2 to my v prime, and I'm getting negative. Since v prime switches from positive to negative at x equals 1.585, we know that a is going to, we know that v is going to have a local maximum at x equals 1.58. That's great news. So we'll go ahead and throw this on an XYT chart and evaluate. So we've got our x, v of x, 0, a, 4.25, and we'll go ahead and evaluate now. And so, again, I'm not going to graph it, but I am going to evaluate it several times. So I'm going to do my original 4x. X cubed minus 39x squared plus 93.5x. And I'm going to go to my table. Oh gosh, must have been in advanced algebra. I like the ask. 0, alpha A, 4.25. 0, 66.148. Cubic inches. And 0. So who's the big winner, Mikey? Who's the big winner? Looks like my x dimension, height of 1.585. Produce the maximum volume possible of 66.148 cubic inches. And the question, though, wasn't what's the max volume. What was the question? What was the question? You guys have it. I don't have it. So our dimensions. Oh, so we've got to do length and width times height. So dimensions would be easy now that I stored this in alpha A. Hey, I'm sure glad I stored that in alpha A, because now I can just do on my home screen 11 minus 2 alpha A. There's my length of the box, and I can do 8.5 minus 2 alpha A. There's the width of my box, and then what's the height of my box? Well, that's the alpha A, the 1.585. All right, guys. So final answer, the box dimensions to maximize the volume in such a way would be 1.585 inches by 5.329 inches by 7.829 inches. Good thing we used calculus, because it sure ended up just being a whole number, 2 inches by Allie.
Does it matter what order we put the numbers in?
Nope. Rectangular solid area, okay. Awesome. What questions you guys have about the open box problem? Then I do have the fish tank answers done complete, but we're not going to take a look at it now. So what I want to do instead is go ahead and close up our discussion today. And so let's go ahead and write down our 3 tools, be ready to share with the class. So a written response for each. What are the 3 tools that can help us find optimal solutions? And then summarize the optimization strategy and be ready to share with the whole class. I'll pause the recording while we write. Okay, go ahead and share one tool that we can use to find optimal solutions in our optimization strategy. What's one tool that we could utilize? Nikki?
The first derivative test.
The first derivative test, right? Let's make our y prime number line analyzing increasing versus decreasing behavior of original function. Good. Thank you. What's a different tool that we can utilize? Peter?
Closed interval method.
The closed interval method, right? The closed interval method is make an XY chart and compare the Y coordinates with my endpoints and the critical points, and then analyze the situation to determine your extremes. And our last test that we didn't use today, but still at our disposal, is what, Scott?
Second derivative test.
Good. Our second derivative test is another tool that we can use to find local extrema. All right, let's go ahead and summarize our strategy. So we've got step 1. We want to, Michaela?
Write the goal.
Right, we want to write down our goal quantity to be optimized. So we're going to write our goal. What quantity are we trying to optimize? Step 2, Blake? Good, we draw a picture and label. Good. Step 3, Paul?
Write an equation that meets the goal.
Good. We're going to write a goal formula for the quantity to be optimized. Step 4, Amanda?
Write the formula as a function.
Good. So we'll rewrite that formula as a function. Awesome. Step 5. All right, what are we doing? Step 5. Allie, why?
Use closed interval method or first derivative test.
Good. So use tools, right? Use tools to optimize. And lastly, what's our step 6 tell us to do, Vivian?
Answer the question.
Good. Answer the question. Don't forget to include your units, right? Answer the question that was asked. Way to go, you guys. I'm going to say answer questions with units. Strong work, you guys. All right, so let's take a look at our schedule briefly. So here we are today, day 3, optimization, next class period. This is Monday, Tuesday. We're going to look at more optimization. Thursday, Friday will be some review time. We're going to take a look at some multiple choice practice and have some review. We'll also take a look at some change of limits and some hodgepodge stuff to get us ready for the AP exam. And then we've got spring break, right, sandwiched in between our review and then our Unit 8 test. So that can be good and bad. Let's make it good, right? Let's make it good. So you've got your resources in advance. You're going to have your concept and skill guide. You have all your materials. Just make sure you're being smart about your preparation and setting aside some time to make sure you're ready to go when you return. Awesome. We're going to go ahead and stop the recording and post it to our Moodle site.